Remember that? And the renal veins. Renal arteries carry blood into the kidneys, and renal veins drain blood from the kidneys. That should be easy for you to understand. The amount of blood per minute that goes into the kidneys, that's called renal blood flow. Doesn't that make sense? The amount of blood in and out of the kidneys, renal blood flow. Never a down up motion. Renal blood flow. Blood in and out of the kidneys. Now, what is the job of the kidneys? We can reduce the job of the kidneys into the following list. Filtration. There's stuff in your blood you want to get rid of. What are the ways out of your body? How can you get things out of your body? List the ways. Pee it out, poop it out, under normal healthy conditions. Pee it out, poop it out, sweat it out, breathe it out. Most of us are not sneezing. Achoo, achoo. Maybe Ashley, but most of us not. Now, of those four things, are you sweating profusely right now? And do you all the time? No. No.
My sister would have to disagree with that. You should be my dad.
But do you think that's a help? Throw me a bone! Do you think that's your major way of getting things out of your body under normal circumstances? No. How many times do you poo? Twice a day, maybe.
Too much, bro.
One in the morning and one in the afternoon.
I told you we have competitions in my house. Anyway, most of us think of breathing or urinary, right? Those are the things we do the most through the day under normal, healthy circumstances. All right, well, we've already covered breathing. That's where we get rid of our acid in gas form, CO2. But there are also other acids for metabolism that can't get out in a volatile manner. That means gaseous phase. They're called fixed acids, and the only way to get them out is through your urine, at least in copious amounts. All right, well, that means filtration. You got to filter your blood to remove them. Then there are some things dissolved in your plasma that get through this filtration membrane, very similar to your respiratory membrane, that are good. And you don't want them to end in the toilet. What are some things that are dissolved in your plasma along with waste that you want to keep? Nutrition like what? Electrolytes. Those aren't necessarily nutrition, but very valuable for excitable cells. Keep going.
Calcium.
That's an electrolyte. Glucose. Amino acids. Those are freely filtered too. They're on their way to the toilet. You want to keep those. They were part of your blood. You now filtered them. They're on their way to the toilet. You want to take them back into the blood. The action of taking something back into the blood is reabsorption. Then there are some things that are so bad, or your body just says, look, this is a waste and we really want to get rid of it, that filtration's not enough. You want to be able to take it from the blood and put it into the nephron. And this is in addition to filtration. So we have filtration, reabsorption, secretion, and the output of all three of those functions is what comes out in your urine, what you excrete. When we are worried about renal function, we say whatever you excrete in your urine is equal to whatever you filtered in the first place, minus whatever you might have reabsorbed, because you're not going to then have it in the toilet, plus whatever you secrete, whatever you really want to get out of your body. That's the function of the kidney, right there, in one equation. Who said there'd be math in biology? There is. Here is a blood vessel carrying blood to a capillary bed. We know now that capillary beds are called your exchange vessels. But in the kidney, we're going to see a capillary bed in tandem. Ashley.
Is this the whoosh? Is this the thing where you were like,
Yeah.
oh, okay.
Mm-hmm.
From the beginning of class?
Yes. So we
It's like
have
you wanna
blood.
do-
Let's just pretend this is the renal artery for right now, just for learning purposes, just beginning. We have blood coming into the kidney, renal artery, not E, renal artery. It's going to write renal. It has to come into a capillary. This is where filtration is going to occur. It's a similar thing to you making coffee in the morning. How do you use a coffee pot to make your coffee? You put in a filter, you have the grounds, and you have water pass over it. I want you to think of this as your filter, and you have water coming in the form of plasma, and some of it is going to get out into your coffee cup, and that's what we call urine. But before it gets out as urine, in here it's technically called filtrate. So we have blood arriving. Some of the plasma will get into this structure called a nephron, and that fluid is called filtrate. You can't call it plasma because it's not identical to plasma. And as this filtrate goes through all these structures of the nephron, the composition is changing. And on your lab exam, I'm here to tell you, they will ask you, where along the nephron is the filtrate most like plasma, and where is it most like urine? Doesn't it stand to reason that any structure closer to this capillary bed means that filtrate will be the most like blood? Mm-hmm. Any structure further away from this would be more like urine. Okay. You all should know your anatomical terms, proximal versus distal, right? When I say proximal or distal, I'm asking you to relate to this beginning part. This is the beginning. This is our starting point. This is where we first get our filtrate made in a process called filtration. The blood is arriving, and some of the plasma is going into this structure called the glomerular capsule, sometimes referred to as Bowman's capsule. I will switch between them. Glomerular, G-L-O-M-E-R-U-L-A-R
I-A-N.
G-L-O-M-E-R-U-L-A-R capsule. So we have filtrate in the glomerular capsule. It's derived from plasma, but it's not identical to plasma. What gets through? We have whole blood showing up in this capillary bed, a very special one called the glomerulus. That's what that is, the glomerulus. You have whole blood showing up. Jim, are you urinating out blood right now? Good. You shouldn't be. Females in this room, are you urinating out blood right now?
No.
None of you should be. Even if you are menstruating. That comes out a different hole. More on that in the next 2 weeks if you're confused about that. Pay attention in the next 2 weeks if you're confused about that. Really, actually, some people are quite confused about those different holes down there. And they didn't always teach about sex in schools. And some couples have been infertile because the man was using the wrong hole.
What?
Yeah. And the woman couldn't figure out why she kept having UTI infections.
Oh.
Yes, it can.
Without like excruciating pain?
Yes, very very painful.
Then
That's
why
why.
would you continue with that process?
Because people don't know, and they didn't talk about it. They didn't talk about it.
I refuse to accept that people couldn't figure. I mean, those must be the same people who can't find America on a map.
No. Very, very reserved, sheltered, religious. No, I am telling you. Just not educated. I mean, if you never had a book and someone never showed you this hole is for this hole is for that, how would you know? Yeah, I'm telling you. My Chinese graduate student coworker, when he got married, he said he went to the library and checked out books so he would know which hole to use. I'm not kidding. And he.
Just from an evolutionary stand, how is that even feasible?
I understand, but then arguably, those people who couldn't figure it out are not as fit, and they didn't pass on their genes.
Well, we shouldn't have any of those people left.
I know, it staggers the imagination, but I'm here to tell you, it has happened. I'm not saying in great numbers, but I'm telling you, there are couples who are infertile because of that. All right, so to get back, it's okay. It's what's to come when we actually get to the reproductive system. I mean, you all, there will be question. So we have whole blood here. We all agree you shouldn't be urinating out red blood cells, right? So whole blood, remember, is formed elements and plasma. Formed elements are not getting through the filtration membrane. But plasma and what's dissolved in plasma, by large part, does get through. What doesn't get through the filtration membrane? And what is it in the first place? We have simple squamous endothelium, simple squamous epithelium with a fused basal lamina in between. Where have we heard that before?
Respiratory.
Respiratory. It's the thinnest possible membrane. And there are holes, slits called fenestrations, and this creates a capillary with high permeability. Remember in our Unit 3 you learned about continuous capillaries, fenestrated capillaries, and sinusoidal. And I said continuous is the most abundant, sinusoidal most permeable. Fenestrated, we're going to see this in certain areas of the body, and they provide greater permeability. Here you are. Here's your fenestrated capillary bed called the glomerulus. Ashley.
So are they fused then, since they have the...
They share a sheet of protein between them. Yes. So that sheet of protein is a barrier to plasma proteins from going into the glomerular capsule. Most anatomy instructors and some textbooks say the fenestrations, the slit-like holes, are too small to allow plasma proteins to be filtered, and that's not true. They are many times larger than plasma proteins. They could let them through. What acts as the barrier is the sheet of protein called the basal lamina, and that's because that sheet of protein has the same charge as the plasma proteins, and same charges repel each other. If a person has that basal lamina starting to degrade because of a disease process, we will start seeing protein in their urine because it can get through. And that's not good. You shouldn't have protein in your urine.
Really?
Mm-hmm.
Doesn't that mark like a degradation of the kidney?
That is suggestive that your filtration membrane is being degraded, maybe attacked in an autoimmune disorder. It's not good.
How would you tell if there's protein in your urine?
Great. I can give you a cup. You can go pee in it. I'll give you a little stick. You'll dip it in there, and I'll say, you've got proteinuria.
So just from looking at, like...
Just from looking at it? No. But if you all want to go pee in a cup, I can bring those in here. I'll give you the dipsticks, and you can start dipping away and see what you have in your urine.
Let's go. Right now? It sounds fun.
Want to? It's what we do in physiology, don't we, Miriam? Was it very exciting? Yeah, when you have a whole room full of urine cups filled. Oh my. Add to the mix, someone had broccoli the night before, or asparagus. It's awesome. And then in physiology, I give you tablets and you boil your urine to see if there's sugar in it, and that's lovely too. Anyway, it's easy. It takes 30 seconds to find out what's in your urine. It's what they do when you go for a doctor's appointment. You pee in the cup, they take it away. They're using urine analysis dipsticks. And they just have little swatches of chemical indicators. They dip the whole thing in. They can tell if you've got blood in your urine, glucose in your urine, protein in your urine, urobilinogen. I mean, they're measuring a whole bunch of stuff. Really easy to do. All right. So we filter. What part of our whole blood can get through? Plasma. Right. What's dissolved in plasma in high amounts? Well, first of all, it's water. A lot of water. Agreed? Okay. And we also have dissolved in that water, as you correctly said, electrolytes. And the most abundant electrolyte in your plasma is sodium. And in physiology, we say, where sodium goes, water goes. Follow it. Where sodium goes, water goes. Follow it. That works 8 out of 10 times. There's also glucose. There's also amino acids. There's potassium, but in less amounts than sodium. We have other electrolytes too. Now this filtrate goes to this section right here. This is called the proximal convoluted tubule. Proximal why? Closest to Bowman's capsule, glomerular capsule. Convoluted because it twists and turns. And it's a tubule. It has a lumen. And the filtrate is going through this lumen. And there are cells here lining the lumen. And these cells are simple cuboidal. What does cuboidal mean? Cube shape. They are as equally wide as they are tall. And their apical side, that means the side that faces the lumen, has these little microvilli. And to anatomists and physiologists, when we see a cell with microvilli, extensions of its cell membrane, that tells us that's a cell that relies on surface area. What are they putting in their cell membrane? And they're inserting membrane transporters. You learned this in Unit 1. How do we have membrane transport? There's simple diffusion, there's osmosis, there's facilitated diffusion where a protein locks onto something and moves it across the cell. So these proximal convoluted tubule cells, their job is to reach into the filtrate and pull back all the good stuff you want to keep in your body. And if I were to draw these cells larger, this side would be the luminal side where the filtrate's passing by. They insert these transporters on their apical side. And what they do is they reach into the filtrate, move these solutes through the cell, out of the cell, and guess what's all around that proximal convoluted tubule like a net? Capillaries? A second capillary. This is a system of 2 capillaries in tandem. What is that called?
Portal system.
A portal. And this arterial leading to it is called the afferent arterial. Oh, what does that mean? Going in. Into where? The glomerulus. Guess what this arterial is called? Efferent. It is. And because we have a capillary and a second capillary separated by arterioles, this is an arterial portal system. So these cells are going to pull out of the filtrate all the good stuff, the glucose, the amino acids, sodium, potassium. So this is a site that's heavily used for reabsorption. Heavily used. Now in physiology, I teach you about all the different kinds of transporters that are there, and you will have to know them. Right now, it's enough for you to know that this is participating in 100% glucose reabsorption. This area of the nephron is the only place where you have glucose transporters. The only place. And if someone has too much glucose in their blood, where it overwhelms those taxicabs, guess what happens? It continues on. There is no way. This is not a muscular structure. There is no way for this proximal convoluted tubule to go, wait, constrict! We got to get all that glucose before you go to the next segment. There's no way. They are not muscular. You either get it on that one pastime through or it's on to the toilet. That's it. 100% amino acids. How much water is reabsorbed in this segment? Because there is a lot of water reabsorption, about 65%. And how much salt? I'm just going to focus on sodium right now. Sodium, there's 67% reabsorption of sodium. Now let's drink this filtrate. Let's drink it all along here. Drink, drink, drink. How salty does it taste to you compared to the salty flavor of your blood? And it would be the same. We say this provides isoosmotic reabsorption. That means salts and waters and other solutes are being reabsorbed at roughly an equal rate. Let's play. How can you make a solution more concentrated? You have two options.
Take away the solute.
Add solute or take away solvent. Okay? One of those two options changes your volume, though. Which one? The solvent. How can you make something more dilute? Add more water or take away solute. One of those two options will drastically change your volume. Agreed?
Yeah.
Okay. So I want you to know that the kidney, the nephron in particular, plays that game all through the nephron. You have to stop and ask yourself, where am I in the nephron? What is it capable of doing? Because each section has unique physiology, and it's all because of its gene expression, driving what kind of membrane transporters it has. So you have to stop and ask yourself, what's happening? Where am I? What kind of gene expression do I have? What's moving in or out of the filtrate? Here we have a lot of reabsorption. And at the end of that proximal convoluted tubule, we have very little volume left. Most of it we reabsorbed. But even though we have smaller amounts than what we began with, it tastes just as salty as the plasma we started with. We've had equal removal of water and salts and other solutes. Okay? Now the descending limb. Whoosh, we're going down. The descending limb, we've been so used to saying water follows particles. Remember? Particles suck. And when we get to the loop of Henle, or nephron loop, we actually have two segments of this loop that separate solute from water. They have to. Not for their sake, but for the sake of surrounding structure. See, I've drawn this in a two-dimensional feature, but really it's twisted all around itself. Do you pee the same kind of urine throughout the day?
No.
Have you ever looked in the toilet? You should. Is it the same intensity of yellow?
No.
Has it ever been bright orange for you?
Sometimes.
Brown, maybe? But clearly, sometimes you look in the toilet and you think, did I even pee? It felt like I peed. It looks like I could just drink that. And my dog goes, good enough still. Ew. So there are times when we make a urine that's very water-like and times where it's very concentrated. And that's because of this. Being able to separate water and solute. It's what we need. It's because of this loop being able to do that. It's other segments that can then use what that loop did and obey hormones and change the kind of urine you make. You're really dehydrated. What does your urine look like?
Yellow.
Bright yellow, and you produce little amounts of it. You're dehydrated. You're well hydrated. What does your urine look like?
Like your water.
Copious amounts of dilute urine. Your variable types of urine are dependent on this loop doing its job and the other segments responding to hormones. If you disable the loop, you cannot make a concentrated urine. And we do that in patients. We give them diuretics to disable that loop, and they end up producing copious amounts of dilute urine. So what does the descending limb do? The descending limb of the nephron loop reabsorbs water about 20% of what you originally filtered. And here's a weird thing. There's a lot of salt here. A lot of salt. Where did it come from? To be continued. Where did this salt come from? All around the outside of this nephron. Very salty. All of this salt, the driving force, because it's so concentrated, we have water coming out. The water's attracted to the salt. But we have a little bit of salt going in. And as this filtrate is going down and these cells are pulling out the water and a little bit of salt is going in, if something's going into the lumen, it's called secretion. As the filtrate is going down to the hairpin turn, tell me what it tastes like. How do you make a solution more concentrated? Didn't you just say you can add more solute or take out solvent? Look what it's doing. Both. And by the time you get down to the hairpin turn, it is as concentrated as you can make it. How concentrated is it? 1,200. 1,200 what? Milliosmolar. What does that mean to you? It's 4 times more salty than your blood. 4 times. That's the maximum you can do. And that means that's the maximum you can make your urine concentrated. When your urine comes out and it looks orange to you, you've done the maximum you can do, and your urine comes out as 1,200 milliosmolar. Why is it only 1,200? Because of this thick ascending limb. There is a thin, I don't care about it. Who cares? It's physiologically boring. Move on. We're just going to treat the ascending limb as if it's thick. Why is it called thick? Because we get our cuboidal cells back. Why do you think the thin descending limb is called thin? The cells are not cuboidal, they are squamous. So in the thick ascending limb, we get our cuboidal cells back. And what are they doing? They're pulling out salts. What are they pulling out? They're pulling out a lot of sodium. Do you remember the sodium that I just wrote all the way on the outside of the nephron here? And I said, where did that come from? This ascending limb with the cells and their protein machinery, they are working so hard. They're pushing out salt there. They're also pushing out some potassium and chloride. But it's mostly sodium. And it's accumulating there because those cells are working harder and faster than the rate of water and osmosis, the rate of water moving. Doesn't that blow your mind? These cells use more ATP than any other part of your body to fuel these protein transporters that are moving these salts. What do you think would happen with our ability to put salt in here if we had longer, thick ascending limbs with more cells and more protein machinery? Then we could put more salt here. And if we had more salt here, then we could extract more water and we could make a more concentrated urine. But we don't. Most of our nephrons are called cortical nephrons. And that means they're in the cortex of the kidney, the outer region. Only 20% of our nephrons are juxtamedullary, which means they go deep into the kidney and have long limbs of loop of Henle. If we had more of those, then we could create an even more concentrated urine and drink seawater with impunity. But because we don't, we can't. But a kangaroo rat has more of these long loops of Henle, and that's why they can live in desert conditions. The desert tortoises, same thing. They have more of those long limbs. Isn't that amazing? So what's important about the hairpin turn? This is the maximum concentrated filtrate. How concentrated compared to blood? 4 times. The ascending limb, what's important about that? We are reabsorbing sodium, chloride, potassium. No water. Isn't that weird? We've got solutes leaving, particles leaving. Water's not following them. They are impermeable to water. And this thick ascending limb is called the diluting segment. And it's reabsorbing 25% of the solutes, salts, that you originally filtered. And no water is following. And it's outmatching the descending limb. Drink the filtrate as it goes up. It's called the diluting segment. How do you make a solution more dilute? You either add water or remove solutes. What is the thick ascending limb doing? Removing solutes. Drink the filtrate as it goes up. How does it taste then? It's becoming less salty. And I'm telling you, by the time it gets up to the top, it is now 1/3 of the saltiness of your plasma. That's how hard that thick ascending limb worked. We went from 1200 to 100, and it just plucked out the solutes, the electrolytes. That's amazing. Now we get to a section called the early distal convoluted tubule. I'm drawing some lines here. There are no boundaries. The early versus late. Why is this whole section called the distal convoluted tubule? Where's our starting point? Over here. This is a great distance away. Early, because it comes first, and then the late portion. Physiologically, they do different jobs. In the early distal convoluted tubule, it is still called a continuation of the diluting segment. What does that mean in English? It is still removing salts, sodium chloride only. No water. It is still impermeable to water. Drink your filtrate. What's happening to it? It's becoming even more watery. We don't have as much volume, but we've pulled out the solutes. How much more have we pulled out? 5% of what we originally filtered. Do the math. We've reabsorbed 67% salt in the PCT. In the ascending limb, we reabsorbed 25%. And here, we have another 5%. Where are we? Of your salt that you filtered, you have now reabsorbed 97%. What's going to happen to the last 3%? My question to you is, are you on a high salt diet? Do you need that 3%? Are you on a low salt diet? Do you need that 3%? When you get to the late distal convoluted tubule, this is where a decision is made. Do you need the rest? The rest of what? Salts. In particular, sodium and potassium. Do you need the rest of that water? Tally up how much water we've reabsorbed. We've reabsorbed 65% water in the PCT, another 20% water in the descending limb. We have 85% of our solvent already reabsorbed. How much is left? From here on out, these cells say, do you need that remaining 3% of your salt? Do you need that remaining 15% of that water? What's your diet like? What's your water intake like? And these parts, the remaining parts, are going to respond to hormones. Different endocrine glands are going to say, yeah, we need that salt. Give it to us. Oh no, we need that water. Give it to us. The late distal convoluted tubule, it has two cells. Early continuation, diluting segment, 5% sodium chloride. Late hormonal control, two cells, principal cells and alpha intercalated cells. Do not worry about alpha intercalated cells. You are not ready for that discussion, my young Padawan learners. That has everything to do with acid-base balance. That's for physiology. Principal cells, they're the ones that respond to aldosterone. You should be able to tell me what that does. Oh man.
Increase absorption of water and sodium.
Increases, these cells then increase how much sodium and water they reabsorb. But it comes at a price. What does it secrete? Potassium. So aldosterone, if you're on a high potassium diet, might say, oh, you need to get rid of some of that. Aldosterone also is a hormone where you might need more sodium and water. You're on a low salt diet. You haven't been drinking your water. Now, technically speaking, a hormone called ADH can also target here. For testing purposes, I am drawing a line in the sand. Are you listening? For late distal convoluted tubule, I want you to know there are two cells there, alpha intercalated and principal. Alpha intercalated, acid base. Worry about that later. Principal, they respond to aldosterone. Period, end of story. These are called connecting tubules to collecting tubules to collecting ducts. We're getting bigger. Connecting tubules to connecting tubules to connecting ducts to collecting ducts to medullary ducts and papillary ducts. I don't care about all these. I really don't, and they're not part of the nephron. I focus mostly on your collecting ducts and medullary ducts. These cells here respond to ADH. Without ADH, they're not permeable to water. And yet there's a whole bunch of salt out here. And remember, particles suck. But the water can't go out because they're not permeable. Only when ADH is around are aquaporins inserted. These cells insert their aquaporins, and all the water that is still remaining, that 85%, it's attracted to those particles. The salt on the outside extracts water. Now, how much water is left? We said 15%. Do you think you can completely reabsorb all of that last 15%? No. And still get your wastes out of you? Do you pee cottage cheese like my desert tortoises? No. So there's something called, I'd like to try that just once. There's something called obligatory water loss. You have waste that needs to get out of your body. And like a toilet, you need water to flush it out of you. Depending on how much waste you have, dictates how much water has to go with it. Have you ever gone to someone's house and gosh darn it, you went big potty in their toilet and you didn't realize they had a low flow toilet? So that's happened to you. What do you end up doing? Flushing over and over again because that big amount of waste needs more water to flush it through the pipes. The same rule applies to your nephron. It really does. You have more waste you need to get out, then water has to follow it. And the maximum you can concentrate your waste, like I said, is 1,200. Now, let's do some quick, fun math before I stop this story and you quickly look at some of the nephrons. Because remember, you're going to have a nice long break, right? So I want us going to 5 minutes to noon today. I won't see you again until 12:30, maybe. Remember I have my meeting with my dean? We don't have time to waste. We're at that semester point, we're burning. Okay. You are lost at sea. No water in your boat. Water, water everywhere, nor a drop to drink. Where is that from? Rime of the Ancient Mariner. And in that poem, this guy is on his way to a wedding reception. Creepy old sailor dude says, "Aye, let me tell you about my travels." And young guy says, "I just want to go get my drink on and party with my friends." And the sailor says, "Aye, sit down anyway." That's not really how it goes, but I'm embellishing. This is the party I have when I read literature, right? Try and modernize it. So the guy sits down, and the sailor says, "Oh, we were stuck in the doldrums." Do you know what the doldrums are? No sailors here? It's the areas of our ocean where the currents and the winds are not favorable to inflate the sails or actually have the ship move through the water. So the sails go flat, and there's no oceanic current to really keep pushing you. You're just kind of stuck there until a storm might pick up. So they were stuck in the doldrums. They ran out of supplies. And some of the sailors made some really bad decisions, which brought more bad luck to them. Anyway, at one point they say, "Water, water everywhere, nor a drop to drink." Why not? Why not drink the seawater? It's too salty. But that's not, no, look, you're big boy, big girls now. Apply it to your nephron. Apply it to the idea that you don't have very many long loops of Henle, and that the only amount of salt you can concentrate here is 1,200. The only maximum you can concentrate your urine because of that is 1,200. If you were able to concentrate your urine to 1,200, and if I told you the amount of waste you get out every day is 600, what's the minimum amount of urine you can make a day and still get your waste out? 600 divided by 1,200 is what? 600 divided by 1,200 is 6 divided by 12.
Oh, a
Oh, my land. Half a liter of urine. That's what you must still pee out to get your wastes out. That's obligatory. Now let's play. You drink a liter of seawater. A liter. How concentrated is most seawater? Is it 1,200 like your blood? 2,400. Now do the math. You just drank 2,400. That's extra salt you now need to get rid of, in addition to your 600 particles of waste. Where are you? 3,000. What's the maximum you can concentrate your urine? 1,200. How much fluid will you have to pee out for that 1 liter you drink? Divide 3,000 by 1,200. 2.5. 1 liter of water will cost you 2.5 liters of pee. How much did you drink? Let's do this again. 1 liter. How much are you now peeing out? 2.5. You're going to become more dehydrated than what you took in, and you will go crazy. And people who drink seawater have these mirages because they become so dehydrated, and they jump into the water, and guess what's following them? The wolves of the sea. No, not just any shark, the wolves of the sea. The ones that swim in packs and specifically follow boats because good things fall from them. Blue sharks. Do we drink seawater?
No.
Okay, Bear Grylls. Do we drink urine? According to him, this is a thing to save your life. Okay. Who likes to hike? Do you go out on your hike and say, my bottle of water, but I know I'm going to get lost today. So I'm just going to dump this water out and immediately start saving my urine to drink later. No. When does drinking your urine become a good idea that you even entertain? You've been walking, drinking your water, drinking. I don't have any water. It's okay, I'm on my way back. Wait a minute. Where am I? Okay, I'll just keep walking. I'll find my way. Meanwhile, you've been behind trees. By the time you realize you're not getting home, and you realize you're in dire straits, and Bear Grylls pops into your mind, what do you think your pee looks like at that point?
Really yellow.
Yeah. How concentrated? 1,200. How much pee do you collect if you're lucky? Maybe a half a liter. I'll save this. It'll save my life. Great. Here's your half a liter of your 600 particles that you had to pee out. You're drinking right back in that half a liter. Those 600 particles have to come out, plus the next day's 600. You drink half a liter, now you have to get rid of 1,200 particles, but what's the maximum you can concentrate it? 1,200. And how much will you pee out? 1 liter. How much did you drink of your urine? Half a liter, right? It was a half a liter. To pee out a liter. Yeah. But if you started to collect your urine, say the day before when you were well hydrated, and pack that in your backpack, sure, drink your urine. But then why not bring more water? It's asinine. We don't drink our urine. Stupid. Okay. With those models, I see 2 of them on that table there. There are 3 models on that single plaque. On the right side, you see Bowman's capsule with the glomerulus, with the afferent and efferent arteriole. Which one's which? Afferent has a wider lumen than the efferent. Then in the middle panel, you're seeing nephrons. The little pink balls are representing the glomerular capsule, and you're seeing that the nephron is colored different colors, like a lime green and a peach. See if you can follow where the PCT is versus the late DCT in a descending limb and an ascending limb. Then on the far left model, you're seeing a section through the kidney. You're seeing the outer lighter layer, that's the cortex. The inner layer that's a darker pink is the medulla, and it's arranged in lobes, so you might want to read up on that. And then you're seeing painted in light green some nephrons and the collecting ducts, some medullary ducts, some papillary ducts, and it drips to the internal region of the kidney, and you have collecting vessels. They look like funnels. They're painted in cream. Those are called calyces. The smaller ones are called minor calyces. Then the urine drips into larger, major calyces, into a bigger funnel-shaped structure called the renal pelvis, which then exits the kidney and turns into the ureter. Take some time to see if you could figure that out. And there's a video I did on those. I know for a fact, because that's one we go after. Take some time, please.